Section 6.5, Optimization Problems 2, Exploring Solutions. So once again, we get to explore. Hooray! The goal today is to explore the feasible region of a system of linear inequalities. Explore the math. We're going to be looking at this same problem that we looked at the other day with the sport utility vehicles and the model cars, etc. So a toy company manufactures two types of toy vehicles, racing cars and sport utility vehicles. No more than 60 racing cars and 60 sport utility vehicles can be made each day. The company can make up to 60 or more vehicles, 60 or 70 or more vehicles in total each day. It costs $8 to make a racing car and $12 to make a sport utility vehicle. All this should be familiar to you. Combinations of racing cars and sport utility vehicles that could be made. The company wants to know what combinations result in minimum costs, and what these costs would be. With these optimization problems, that's what matters, the minimum and maximum cost. We're trying to optimize the minimum and maximum. The following model represents this situation. The feasible region of the graph represents all the possible combinations of racing cars and sport utility vehicles. So remember the steps we talked about. Step 1 is the variables. So we've got let S represent the number of sport utility vehicles, let R represent the number of racing cars, and let C represent the cost of production. That's step 1. Step 2 is the restrictions, because we're talking about vehicles, model vehicles. We can only look at whole numbers. We're obviously not going to have negatives or fractions. So restrictions are that S is an element of the whole number system and R is an element of the whole number system. Our constraints, we can't have less than 0. So S has to be greater than or equal to 0. R has to be greater than or equal to 0. We know that they can produce no more than 40 and no more than 60 in terms of the racing cars and sport utility vehicles. R is less than or equal to 40 and S is less than or equal to 60. We also know that they will produce at least 70 vehicles each day. R plus S greater than or equal to 70. Those are the constraints. Step 4 was the objective function to optimize. That had to do with the total cost. We know that it's $12 for a sport utility vehicle and $8 for a racing car. So the total cost will be $12 per sport utility vehicle plus $8 per racing car. Over here, they've graphed it for us. Take a look at how they've done it so nicely. We can see our vertical and horizontal lines that have to do with the S being less than or equal to 60. That would be this boundary right here, and the R being less than or equal to 40. Shading for each of those. For this first one, the S is less than or equal to 60 for the vertical line. The shading was to the left because it had to be less than or equal to 60. For the horizontal line, R is less than or equal to 40. The shading is below. And then for the other one, R plus S is greater than or equal to 70. Now what they would have probably done is find the intercepts. The R intercept would have been 70. S intercept would have been 70. Connect them with the stippled green line and shade. The shading for that one would have been to the right or above, whichever you prefer. So now we can see our feasible region found right in here. How is that going to help us to determine the minimum and maximum costs? I mean, one thing that we could do, I suppose, is pick every one of those points out of there, test it in the objective function, and determine the minimum and maximum that way. That's pretty time consuming, not very efficient whatsoever. What we're going to do, though, is we're going to explore this feasible region. We're going to see what kind of patterns we find, and are there specific points where we're going to be able to easily find the minimum and maximum values. Question is, and this is what you're going to work on tomorrow, is how can you use patterns in the feasible region to predict the combinations of sport utility vehicles and racing cars that will result in the minimum and maximum values of the objective function. Skip ahead to the next page here, and there's some reflection questions for you to work on. This is going to guide you through what you're going to do tomorrow. With a partner, discuss the pattern and the value of C throughout the feasible region. Is the pattern what you expected? So you're going to be taking out from that graph and from that feasible region, you're going to be grabbing some specific points and substituting those coordinates into the objective function to see what kind of pattern you see as you move across, maybe from left to right, from top to bottom, etc. Question B says, as you move from left to right, what happens to the value of C?